Hello, let's talk about section 10.2. We're going to talk about the derivatives of exponential and logarithmic functions. Okay, so for here we want to solve the variable y without using a calculator. So when we have a logarithm, we read it the logarithm with base b, which is 4 here. And then our x is 256. And so we can translate this as 4 raised to some power x is equal to 256. Right, so we want to know how many times do we have to multiply 4 to get to 256? And those amount of times will give me my power x, right? So what we want to do is we want to be able to write the right-hand side as a chain of 4 times 4 times 4, and then count up how many 4s, and then rewrite it that way. So if you don't know your squares, that's all right. We can just start off simple and just take 1 4 out. So 4 times something, we can figure that out by hand really quickly. So 4, right, do the quick division, that gives me 64. Okay. So we know that 4 times 64 gives me 256. So let's continue on. Can I take out another 4? Let's see. So 64 divided by 4 gives me 16, right? And by now, we can also just write 16 as 4 times 4. So we see that on the right-hand side, we have 4 written down 4 times, so we can rewrite 4 to the 4th power. And then since our bases match, and by bases I mean this number that's being raised to a power, since those match, all I do is just say that these are equal. And so my answer here is 4. X equals 4, and basically all this answers is that the log base 4 of 256 is equal to 4, and so originally they just gave it the variable y. Okay? So now for this question, it's a little different, where we were given the base, which is 4, and what the value is, 3. So we can rewrite the log base 4 of x equal to 3 as 4 raised to the 3rd power equals x. Seems a little backwards, I know, but basically we just want to find what x or 4 to the 3rd is. And so x is 4 times 4 times 4. So that's 16 times 4. Could probably also use a calculator on this one too. So x is equal to 64. So that's our answer. All right, now let's talk about some properties of logarithmic functions. So whenever we see a quotient, so x divided by y, we can rewrite this as the natural log of x minus the natural log of y. And that's probably the simplest we can go from here. And then in contrast, when we see a product, we see this x times y, we can write this as the natural log of x plus the natural log of y. And so if you need to remember that, I just remember that the division has this like little bar, so you just know that it goes with the minus sign. Right, so whenever you see division, it goes to minus with natural logs, and then the converse, if you see a product, you just switch it to an addition sign. Okay. All right, so let's do some derivatives now. So let's see, we have derivative. So we have the original function 9 plus 3x plus 8 e to the x And so if I want to find the derivative of f of x, I know that I can break these up based on sums or differences. So the derivative of 9 plus the derivative of 3x plus the derivative of 8 e to the x. Let's see, what else can we do? We know that constant multiples, these numbers can be pulled out. So I can do d dx. This just means taking the derivative. 3d dx of x plus 8d dx of e to the x. Okay, so we know that the derivative of any number, any constant number, is just 0, plus 3 times the derivative of x. The derivative of x is just 1, and then 8 times the derivative of e to the x, and the derivative of e to the x is just e to the x. And so my derivative is f prime of x is equal to 3 plus 8 e to the x. Let's try one more. So we have f of x is equal to minus 15 natural log of x plus 7x squared minus 5. Again, so if we were taking the derivative with respect to x of f of x, we have d dx minus 15 natural log of x. I'm just going to break it up based on the sum and difference of terms. 7x squared minus d dx of 5. Let's pull out any constants I see. So I get minus 15d dx of natural log of x plus 7d dx x squared minus d dx of 5. So now let's take the actual derivatives. So minus 15 times, now the derivative d dx of natural log of x is simply 1 over x. It's a little different. So 1 over x plus 7. So remember how to take the derivative of something with a power on the x. We bring that power down, then decrease the power by 1. So let's bring the 2 down and then decrease the power by 1. And then the derivative of a constant is 0. So if we simplify this, I get minus 15 over x plus 14x. Okay. So now we want to find the equation of a tangent line. So that's going to take the form of y equals mx plus b. Our m is going to come from our derivative at the point that we were given, that's 1. So we first need to find what f prime is. So we can do that real quick. So that'd be d dx of 3 plus d dx of 2 natural log x. So my derivative of 3 is just 0. And then we can pull that constant out, 2. So 2 times the derivative of natural log of x. And so this becomes 2 times 1 over x, or just 2 over x. And then we want to find f prime of 1, so we just plug in 1 into our derivative and we get 2. So then our tangent line looks like y equals 2x plus b. And then now we need to solve for b. And so right now, as we have our equation of the tangent line, we have 3 variables to solve for, but we don't want 3, we just want 1. So one thing we can do is plug in a point x comma y and just solve for b. Right. B. So how are we going to get that point? Well, I know that I do have a point on the function at x equals 1. And so how do I know what the y value is, right? So all we do is we do f of 1, just plug in 1, and this goes in the original function, not the derivative. So 3 plus 2 natural log of 1. Put that in your calculator, or know that the natural log of 1 is 0. So my point here is 1 comma 3. So let's plug that into our equation of our tangent line. So 3 is equal to 2x is 1, and then plus b, and now we can solve for b. And so I get b is equal to 1. All right, but we're not done yet, right? Because it's not asking for b, it's asking for what the tangent line is. So I get y is equal to our slope, which is 2x plus 1. Okay. Alright, so next we want to find the equation of the line tangent to the graph at this function again. Similar type of questions, so we want y equals mx plus b, where my m is going to come from f prime of 0, because now our point is x equals 0. Okay, so my f prime of x is going to be d dx of 3 e to the x plus d dx of 2x. So let me pull out those constants real quick. X plus 2 d dx of x. All right, the derivative of e to the x is just e to the x, nice and simple. And then the derivative of x with respect to x is just 1. And so our f prime is 3 e to the x plus 2. So remember, we want to find f prime is 0, so let's plug in 0 wherever I see an x. So I get 3 e to the 0, e to the 0, or anything to the 0th power is just 1. And so I get the ordered pair 0, 5, I believe. And let me put that over here, y equals 5x plus b. Again, I want to solve for this b, right? And to get that, I know that I have a point at x equals 0 now. So what is y? And that's if I put in 0 in my original function, right? And so if I do that, I get 3e to the 0 plus 2 times 0, 3 to the times 1 plus 2, plus 0 is equal to 3. So that gives me the point 0, 3. So if I plug this into my tangent line, y equals 5x plus b. So if I plug in that point, 3 is equal to 5 times 0 plus b, or my b is equal to 3. And so my tangent line is y equals 5x plus 3. Okay, so now we're going to do some derivatives of different logs and exponentials, but we were actually given, either in the notes or the PowerPoints, these little formulas that I would write down somewhere, just keep handy. So we see that we have a log of base b of x. So when we have this form, the derivative of log base b of x is just 1 over the natural log of b times 1 over x. And I don't think we talked about it yet, but the natural log is just the log with base e. So it's a special form of log, but they are different. Okay, so we're going to use that to answer this question. We want dy dx, and that's going to be equal to d dx of 2 log base 8 of x. Let's pull out that 2 and get 2 d dx log 8 of x. And so this is my b here, that's my base. So if I use the formula that I just put up here, so 2 times 1 over the natural log of our b, which is 8, times 1 over x. And our answer is 2 over natural log, or you can write it this way, 8x natural log 8. I just put the x in front because it's a variable. Okay, so that is your answer for this question. Okay. Now for here we have 11 raised to x. So you may have never seen this before, but that's okay. We were also given this derivative where we have some base b raised to a variable x is equal to b, the base raised to x, times the natural log of b. Now, b is a constant, right? It's not a variable. Okay, because notice how this is different than x to some number. So here we have a variable, and this is a constant. And when we want the derivative of this, we would use the power rule. So bring the 2 down and subtract 1 from the power. So that's different. Notice how the bases are different here. Okay, so let's find dy dx as d dx of 11 raised to x. So we can use this formula again. So my derivative is the base 11 raised to x times the natural log of the base, which is 11. So that's probably the simplest we'll get it as natural log of 11. Okay. Okay, so this one's asking about points of intersections for f and g using a graphing utility. So I'm gonna move over and use Desmos, which is an online free calculator for you to use. Okay, so this is Desmos. It's online, desmos.com/calculator. I'll also include a link in the video description. Anyway, let's graph our first function. I have f of x equals to e to the x over 19. Oops. Over 19. There you go, like that. Zoom out a little. So it looks like that. That's expected with exponential functions. And then my second one is just the parabola x squared. And so we want to find the points of intersection. So notice I have one here, so you can kind of hover over it or you can click on it. And so that gives us a point 6.769, and the y is 45.822. And then there's another 2 places of intersection, so you just have to zoom in a little. So the first, or one of them, is here at this negative 0.2069 and 0.0428. And then the other intersection point is 0.2615, and the y is 0.0684. Okay, so those are your 3 areas of intersection, because you can zoom out really far, and those are the only 3 places where they cross. Okay, and so I believe from our points we got 0.21, 0.04, and then separate the answers with a comma, 0.26, 0.07, and 6745.82. Separated by comma, round to the nearest hundredth, and must be in an ordered pair. So just be careful how you answer that, or put in the answer for this question. All right, so now let's look at the next one that's, I think, similar, right? Points of intersection of these 2. So let's hop over to Desmos again. Now we have the function natural log of x, all that squared. So you can just go into functions, miscellaneous, and then natural log should be right here. Type in your x, and then just be careful that the x or the squared is acting on the entire function. So I'm just going to be short and put it in parentheses like that, like they have it. And then our second function is 7x. So it's just a line with slope 7. And so it looks like that. We can zoom out and just agree that there seems to be only one area of intersection. So let's zoom back and decide where it is. And so Desmos is telling me it's at this point, 0.26, and the y is 1.818. So for this graph, we only had one point of intersection. That was at 0.26, 1.82. Okay. Okay, let's do some last two application problems. So we have a salvage value, S in dollars, of a company yacht after T years using this formula. And we want to know what's the rate of depreciation in dollars per year after 1 year. So we're talking about rates, so this is probably going to involve S prime of T. What do you think? So let's take the derivative. I notice that I kind of have that situation again where I have this constant raised to a variable, which is not a variable raised to a constant. So we're going to use d dx of b to the x is b to the x, natural log of b. So if I want to take the derivative, this is a constant, so I'm just going to multiply it, keep it on the outside, and then now I'm going to take the derivative of this part. My b is 0.7, so 0.7 to t, which is our x in this case, and the natural log of my base, which is 0.7. So I would keep it like that. Don't try to evaluate this and then multiply it by this constant, because you might get rounding error. I would wait until you plug in these t values to round. But anyway, so pretty much all three of these questions are the same. We just want to know at different times. So basically, we just need to find S prime of 1, S prime of 5, and then S prime of 10. And so we're just going to plug in those t values into our derivative. Oops, 0.7. And then so the first one's 1, natural log of 0.7. This one's 30,000 times 0.7 to the 5th power, natural log of 0.7. And this one is to the 10th power. All right, so now would be a good time to throw it into the calculator, because I bet you could not do that in your head. I sure can't. And so I get negative 74,901.74. Remember rounding to the nearest cent. So again, especially with the constant e, you're most likely going to get a decimal. So please pay attention to where you need to round for these quizzes and for the assessment. All right, so for the second one, I get negative 17,983.91, and the last one, negative 3,022.56. So those are your answers there. All right, and then now we have a formula for the relationship between weight and blood pressure in children. So this P of X, and the first question's asking for the rate of change at the 60-pound level, and the second one's rate of change at 90-pound. So it's very similar to the last question where we first want to find P of X, or P prime of X, and then plug in these two values. So P prime of 60, let me put that over here, P prime of 60 and P prime of 90. So let's first find P prime as our derivative. Notice that I have this natural log here. Remember that the derivative of natural log is 1 over x. I think I'm also going to multiply this constant through just to make it a little easier. So if I multiply that 17.4 by both terms, I get p of x is equal to is equal to 139.2 plus 17.4 natural log of x. All I did was just multiply that 17.4 by both the 8 and the natural log. And so now let's take the derivative of p prime. So the derivative of 139.2, that's just going to be 0. And then I'm going to keep that constant, 17.4, outside and just take the derivative of natural log. So when I do that, I get 0.74 times 1 over x. And so my p prime of x is 17.4 over x. And then the last two steps, I just have to plug in 60 and 90 and see what I get. So 17.4 over 60, I get 0.29 rounded to the nearest hundredth. And then for the second part, 0.4 over 90, and I get 0.19. Okay, so that concludes section 10.2, and we'll see you for the next one.